Well, welcome back, everyone. Looks like it's time to officially start. Looks like a small class, but we'll still get through it. We've got 3 people in person, 3 people on Zoom, so that's at least a tie. Before we get started, any questions at all, folks? Okay, well, we're not doing anything too different today, at least not in section 11.10. We looked at mostly Maclaurin series, so now we're changing gears and taking a look at some Taylor series. And then section 11.10, we'll look at some applications of dealing with these Taylor series. So first, here's where we left off on Wednesday's class. We derived a Maclaurin series, which means it's implied this is centered at 0. And it was for the exponential function 5 to the power of x. So just for a quick rundown, since we're about to do it all over again, this is like our warm-up. The methods are, let's zoom in on that just a little bit more. First thing we do is come up with a 2-column system. One column is going to be the derivatives. Other column is going to be the evaluation at the center. And our whole objective in this process is to use what you see right here to come up with that right there. So we want a formula from the nth term. That's what we were practicing all the way back in section 11.1, but it seemed like a smaller problem back then. At least that kind of work really does have a purpose. It's for Taylor and Maclaurin series coming up with those patterns. But once you have the formula for the nth order derivative at the center, the coefficients, Cn, is just implying you divide by n factorial. And then once you're down here, you're basically home free. You take this, the formula for the coefficients, plugs in right there, and now you've got your Maclaurin series represented this way. The steps below is just using the ordinary ratio test to determine its radius of convergence. So sometimes these problems are not too bad. The pattern looks pretty direct. Other times it is rough, I'm not going to lie. And I think the ones that are the roughest are the ones that are deal with a trig function or a hyperbolic trig. So we'll try one of those out again. But any questions at all, folks, with this process here? Okay, so let's move forward then into the new.
I had a quick question. We started using the term radius. It seems like yesterday. And where's that come from? I haven't read the book yet, so if it comes up in the book, I guess I can.
Up in section, let me see here. I believe it was 11.8 the first time. The radius of convergence.
Okay.
This topic right here. So there was the 3 different outcomes of what could happen. Your radius is either 0 if it only converges at the center. It's infinity. This is what happened like on every problem so far in those notes. If it converges for all x. And this is the wonky case where the radius is finite, less some value here. And so you have 3 different, or rather 4 different kinds of intervals of convergence. So it was actually a long time ago, 11.8. It's when we were first looking at power series like these. We didn't even call them Taylor-Maclaurin series, but they actually were. But thanks for asking about that. That's a good question on these notes.
Is there a reason why they use the word radius? I just think it's circles, and I'm having a hard time applying it, I guess.
Yeah, there is a good reason. And circles is the right analogy. It's not a full circle, but we still have the idea of a diameter and a radius. So it's the interval that we're really looking at. When we say the radius is 1/5, for example, and we have a center at 4/5, we plug in the center right here. That's a guaranteed convergence. And the radius is the distance from the center that you're guaranteed to converge on. Does that make sense there about that radius?
Yeah, that makes sense.
So the whole length would be a diameter. Again, that seems like a weird analogy, right? Because it's one-dimensional, but it still has the same kind of thought. There's the center, and there's like the boundary of if it was a circle. These are excellent questions. Other questions so far? Okay. Also notice in these problems, when we're giving the radius, infinity is terrific. And I think we're going to get infinity on this one as well, but not that one. This one does not have radius of infinity at all. It's a finite radius. But in these problems, we're actually just going to be okay with the radius. We're not going to go forward in the work of determining the interval of convergence by testing the endpoints here and here. So in order to make the problem just not humongous, we'll be satisfied with the radius on this one here. Other questions so far? Okay, well, let's try out now, instead of a Maclaurin series, which implies center is zero, so we plug zero inside the derivatives, let's go over to Taylor series. Same exact kind of problem, really. It just has a different center. So for the Taylor series, we'll find the Taylor series using the definition of the Taylor series. That means we have to go through the derivation of the two-column system to come up with the formula for the nth order derivative. And we'll find the radius of convergence at the very end. That highlighting is mainly for me, so I don't forget to do it. We have a center at pi, and so we begin just as before. Let's write these out as a sequence of steps again, just for the reminder, this is a good process to get started. Step one is the two-column system, where we take f of x, which is cosine x, and the next column, take f at pi. That's going to be cosine pi, giving us a -1. Then for trig functions, I usually go with at least 5 rows because of the fact that these alternate in 0 versus non-zero values. So next we need a derivative, f prime of x. We get a negative sine x out of that. And that means f prime at pi. Sine at pi, whether it's negative sine or positive sine, is just 0. So second order derivative next. We have derivative of negative sine x coming out as negative cosine x. So now f double prime at pi is going to be +1. And so far, so good. Now at the third order derivative negative cosine gets us back to positive sine. So now we have third order derivative of f at pi back to 0. And it looks like these are going to be repeating in 6 steps of 5 altogether. The last one is the fourth order derivative at x. It's the derivative of sine x, getting us back to where we started, cosine x. So the fourth order derivative at pi back to -1. So that's our setup so far in step 1. Any questions at the moment with running through that? Okay, so because this is a tricky problem, let's take a look at our indexes as well. At an even value, we have 1. At odd, we have 0 for the derivative. We're mostly looking at the right column. At another even, it's not, I said 1 above here, but it's -1 at top, 1 down below on here. At the next odd, it comes out as a 0, and the next even, back to -1. So we need to split these off, but one thing we can say is if n is an integer, two n is even. One way to think about that is any even number can be divided by 2, essentially. So you could write it as 2 times something. And 2n plus 1 is odd. So the odd values here are going to be this one. If we did another row, it would have been the very next one. These are the terms that we're going to delete in our series so that we can write a series involving not non-negative terms, the actual stuff that varies and is not negative. And it's actually a pretty important step because if we don't eliminate these, we now need a formula like that right there that has to go 0 for one term, non-zero on the next term. It would be a more complicated kind of setup, I would say. So next step, we can now write, let's say something about maybe the odds first, because these are the ones that go to 0. F at any odd derivative, 2n plus 1, put a 0 there, for example, to get to a 1, put a 1 in there to get to the third order derivative. Evaluate at the center pi is always 0. That means the coefficients at index 2n plus 1 are also 0. We're eliminating all of the odd coefficients now by this line. The evens do survive, and they do have an interesting pattern that we're trying to hit. So we're looking at these ones now. So next we write down f at 2n, so an even order derivative. Evaluate this at pi, and that's going to give us, well, here's where we do the pattern. Any volunteers for what we could try here? Well, if we went for absolute value of 1, we would never get the negatives. So we need to somehow alternate from negative to negative in that kind of cycle. In other words, we need an alternating sequence. Yeah.
Just negative 1 to the n, negative 1 to n minus 1.
Let's see, n minus 1. We plug in 0 to start. We would get negative 1 to power negative 1, but that would be negative. I think actually we'd be good with just to that right there. Because if we start by plugging in a 0, oh, hang on. No, you were right. That was a +1. For some reason, I just had a micro sleep or something there. Yeah, good call. That should have been -1, n plus 1 or -1. Let's go with the -1. And that looks like it's it, right? It's just an alternating sequence in that way. With the -1, good call on that. We're starting at a negative and then going positive. But notice when we're doing this, we are also re-indexing. This is going to turn into the new index. So this will be for n is 0. That'll give us a -1 from here. This will be for n equals 1. That'll give us a +1. N equals 2. That would be a -1 to power 1. So back to negative. So in our re-indexing, this is going to give us the right format. So we've got f of 2n down. Now, once you get this, we're going to now go to the coefficient. I think we use blue color coding for this. C at 2n. So all the even coefficients is what we're writing. Formula will be take the even order derivative, f at 2n at pi, divide by 2n factorial. One thing that's easy to kind of miss on these is, if you have a 2n here, it's going to give us a 2n in the factorial, and we're talking about the even order derivatives f at the 2n as well up here. But once we put all that together, this is all we're getting, just -1 power n minus 1 divide by 2n factorial. So that's our format for all of the coefficients in this Taylor series. So that was step 1. I forgot to say, this is step 2. Come up with the coefficients. Finally, step 3, we just put it all together. Any questions first before we write out the Taylor series? Okay, finally putting this all together, we can say, what function was it? Cosine at pi is going to now be a summation as we go from 0 to infinity of c2n times x minus pi to the same power 2n. Just like we match the index of the coefficient to the factorial and the order derivative, over here, if we're only giving the even ordered coefficients, the power here on the x minus the center should also be the same, 2n. It doesn't hurt to throw another arrow there. There we go. So finalizing this, we have a summation from 0 to infinity. -1 power n minus 1, 2n factorial, and that whole quantity is multiplied by x minus pi to the power 2n. We need to come up with the radius, but it's not a bad idea to just kind of eyeball it and see what you think it'll be. In my opinion, if there's a factorial in the denominator and nothing stupendous up in the numerator, it ought to be infinity again. We still have to, for the sake of full credit on assignments on exams actually show this, so we need a ratio test. Those ratio tests, they're really not a big deal once you've done it like a few dozen times at this point, I'd say, at the course. So this is the major work right here, getting to that step. Any questions before we go to check out the ratio test? See if the radius is actually accurate?
Not much of a question, but the more of an observation. So this will, each term of this will model closer and closer the function cosine of x starting at pi.
Yeah, absolutely. I'm glad you mentioned that. So the thing that's new this time is when we go y equals cosine x, and if we're interested in values around 0, this is not going to really help us out, right? Like you mentioned, this is a model more accurate at pi. So right around here, right around, well, about there. So let's plug in a few terms on this just to see what would happen. You'll notice that it doesn't look like it's very accurate out here, but it's going to be very accurate around here. Let's see how it plays out. So we'll go y equals. Let's expand this out a little bit more. If we plug 0 in here to start, we're going to get -1. So that's our first approximation to the cosine function at pi. Doesn't look very great. But at least it matches at one point right here with a true function. Then next we put in 1. When we plug in a 1, we're going to have plus x minus pi. A 1 is going to give us 2 factorial in the denominator. So it looks about like that. That's an improvement, I'd say, not a huge one. So let's put in another term. But notice how bad it does around 0. It's terrible. This Taylor series is only effective if you're nearby the center at pi, like you were mentioning. So let's show one more term. It's going to be a minus now. We're plugging 2 inside here. So this is going to be x minus pi to the 4th power, divide by 4 factorial. And it starts to kind of actually match around this curve even a little bit better. How about one last term? It's kind of tempting. Let's go plus x minus pi to the 6th power. Remember, we're only doing the even terms. This is plugging in 3 as our next index for n here. We divide by 6 factorial. And this is our next step. Doesn't look like it's really converging very rapidly, though. Looks like this one actually involves loads of terms before we get very good accuracy here. But it does seem to be doing better and better as you go. I mean, just delete terms, you can see for sure. Other questions about the convergence that we're seeing here with the finite terms?
Is the idea that if we had infinite terms that we would match cosine of x?
Exactly. As this goes off infinity, this blue curve matches it perfectly, and it does even more. It's gonna, wow, look how that goes. It's gonna match it perfectly all the way around, which is pretty impressive. But cosine looks like it's a pretty tricky function. I might need to put down something like 50 terms to see a really good approximation around here. But yeah, that's the absolute idea. In the limit, more and more terms you put in, the better and better this approximation gets. And at how many terms do we put in? Looks like about 4 or 5 of them. If you're nearby pi, man, looks like you need a lot more terms still on this one. Looks like a pretty tricky power series.
Yeah, I'd be curious like how many terms it would take to get like a radius of half pi or something like that. It seems like it would take hundreds.
On this one, it definitely does. And there's a lot of really cool things you can do with just a basic for loop where you make it add more terms, calculate the distance between the function and a certain range. And if your tolerance is bigger than what you want it to be, the system can just keep on adding more and more terms until this is as accurate as you want. So that's getting into a course called numerical analysis, where they get all into those kind of topics, numerical integration, approximating these kinds of functions, and so on. But that's the value of this kind of thing. And again, you pull out just an ordinary calculator like this one and do something like, say, cosine 3 The way the calculator did it is a modification of just doing the right kind of Taylor series at the right center to give really great accuracy at cosine 3. They're going to give more terms than what we did right here, but it's pretty impressive that this calculator, it's a pretty old chip inside this, can do that all that kind of work pretty rapidly.
So it's performing the Taylor series in the background, the exact thing we're just doing?
Not exact, it's got a modification of it. So there's a lot of extra numerical stuff that goes into it. But this is the heart of the idea of what the calculator is doing. It's taking all these ideas and modifying it to do those computations.
Yeah, interesting, because it only has to go to like 9 decimal places, right? So it makes it a little easier for the calculator.
Exactly. So it gives us pretty good accuracy, even with all those places right there.
Well, doesn't it just have to be the one index, not go very far? Because it's just one that single point right there, right?
Oh, sorry, you're for the cosine 3?
Yeah, it just wants, like n equals 0, right? That's all it needs to get that single point, right?
Well, the single point would be right at pi though, not at 3 itself. So at 3, we're trying to get this value.
Oh, okay.
We're trying to land at, if I can hit a 3, that's really hard actually. We're trying to get negative 0.9899, but our approximation gave us, negative 0.9891. We're zoomed in really far on this, so it's actually a little bit better than it looks like. So we're pretty accurate at 3 if we do a Taylor series centered at pi on this graph right here. But other questions so far? And yeah, you're right, absolutely as well. If you put in, say, cosine, put in a pi, it's not doing anything fancy at all. It just, that's a known value for that one. It's these tricky ones where the calculator, it's working actually pretty hard to get those values out. Well, let's try out one more, and then we'll see what goes on in the pretty much the application side of Taylor series, 11.10 part 2. So this is our last one for the notes. This one is a little bit trickier, so this is a good one to take a look at, to be careful with. What makes it tricky is not the problem where we have some terms that go to 0 and some terms that are non-zero. This one has a different sort of problem. There's one term that's just kind of a combo breaker, and we have to account for that when we go to write out the series. So as before, we start off in the same exact way. Take f of x is natural log x. Evaluate f at the center. On this problem, it's 4, to get natural log 4. Then we just proceed through derivatives. F prime of x is 1 over x, but we have to take a lot of derivatives, so it might be better to visualize it this way. X power negative 1 just makes the power rule easier to work with. So f prime at 4 is then 4 power negative 1. And notice this doesn't look like a very good pattern at all. We have natural log 4 to something totally different, the reciprocal of 4. So that's where the pattern seems to break. But if we keep going more and more derivatives, some kind of pattern should emerge. So here's the second order derivative. We'll get negative x power negative 2. So f double prime at that value is just negative 4 power negative 2. Rinse and repeat. So third derivative is going to be positive 2 times x power negative 3. So over here on the right, third order derivative at 4 is positive 2 times 4 power negative 3. There does seem to be a pattern so far that I'm picking up. Notice that the third order derivative has power negative 3. Second order has power negative 2. First derivative has power negative 1. So that's a nice pattern in there. There's also something else going where it looks like some terms positive, some terms are negative. We might be alternating again. Let's do one more derivative before we finalize any kind of formula on this one. So fourth order derivative next is going to be differentiate this. It's negative now, so negative 2 times 3 times x power negative 4. Then the evaluation at the center gives us -2 times 3 times x power -4. And if we see the pattern, we really shouldn't have to compute too much more. Anyone happen to see what the pattern should be for Fn at 4? I think it's a tough pattern to spot, to be totally honest, because at index 1, you have something that doesn't match up like at all, right? So that's kind of awful. But that's okay. When that happens, we're going to give a pattern that starts with, that goes like this rather. Fn at 4 equals, we'll come up with what it is, but we'll assert that this is only valid for n greater than or equal to 1. So we have one term here which doesn't fit the pattern. It means we have to add in natural log 4 and then plus the Taylor series at our last step. That's easy to forget. Don't let me forget if it appears I'm about to. But we still have to come back here and finalize this. But notice if you've got 2 by 3, that's a 3 factorial, right? And if we took another derivative, 4 would come down. It'd be 2 by 3 by 4. That'd be 4 factorial. Yeah, go ahead.
I was gonna say, is it n minus 1 factorial?
It is, good call. So right over here, we've got an n minus 1 factorial. We also have alternating terms, so we can say, let me add just a little bit more space there. N minus 1 factorial comes into play. Good call. If this is the 4th order derivative, and that's 3 factorial, we're looking at 1 less factorial from that index there. In front, we have -1 to a power, and, oh, hang on, sorry about my indexing. I like to start at 1, I guess, but this should have really started at 0. Let me put in that color to indicate that mistake. We're starting at index 0 and going 1, 2, 3, 4. This part is still correct. We're starting at n equals 1 and going forward. But this was a little bit jarring because I was visualizing putting 1 right here. We have to come out with positive. So this should be n plus 1. So we'll square -1 when index is 1. Plug in 2, we'll get -1 to an odd power. So we really get the negative. So we've got that factorial, we've got the negative, and now, oh dear, that's another typo there. When we plugged in 4 into the 4th order derivative, it went in there for x, so it's times 4 to the power -4. So those 4's carry down, and in our formula down here, we'll go 4 power -n. So that's the format, and sometimes it's hard to be sure if it's really right, so you could do a little bit extra work over here. Looking at this is -3 factorial times 4 to the power -4. This one is just a 2 in front, but 2 is equal to 2 factorial. So we could say that this one is 2 factorial times 4 to the power -3. The negative in front, this would be equal to -1 factorial times 4 power -2. This one has a 1 in front, but 1 is equal to 0 factorial times 4 power -1. But once again, the very first term just doesn't fit this pattern whatsoever. But at least all of these seem to convey down here in the right way. It's alternating. The factorial is 1 less than the order of the derivative, and we have 4 to a negative power, -n. Well, any questions, folks, to this stage? Okay, if we're happy with that, we can now say, let me scroll just a bit. The index, Cn, we're involving all the indexes, but n has to be bigger than or equal to 1 again, because these are coefficients, because on the first index n equals 0, the actual first coefficient is natural log 4. And the rest of the coefficients are going to use this as its pattern in the numerator. So we say Cn is equal to -1 power n plus 1, n minus 1 factorial, 4 to the power of -n. And when we write out the coefficients, Cn, we always divide by n factorial in that kind of way. So we just plug in the prior step here, divide by n factorial. But notice there's also a simplification this time. We can take and write out, let's do this on the margin, n minus 1 factorial over n factorial can simplify like this. Keep n minus 1 factorial just as it is in the numerator. Expand your n factorial in the denominator. It would be n times n minus 1 times n minus 2 and so on. But we only need to go down to n minus 1. Plug in the factorial. And this will reduce to a 1 over n. So that's a pretty big simplification on this. We get -1 power n plus 1. These two cancel to just an n in the denominator. And just to clean it up a little bit, we can take the negative exponent and throw 4 power positive n down below. But once again, this is only valid for n greater than or equal to 1. So we have natural log 4 right here, but as n goes from 1 to infinity, these are the coefficients finally. What we're ready to just write out the full power series, we can say natural log x, the original function, is equal to, I think we need a special color for that. Grab this up here, natural log 4, and that's our very first term. Because it's our very first term, we're starting at index 1 in the summation. We go summation and goes from 1 to infinity. And then plug in the rest. So we've got -1 power n plus 1 divided by n times 4 to the power of n. It's multiplied by x minus the center. The center is at 4. It's the value that we're plugging in when we evaluate the derivatives. So x minus 4 to the power n. We'll still need a radius on this, but this was the hard work, getting to just that step. Any questions, folks, so far? Okay, this one's a little bit trickier to determine the radius on. There's no factorial function in the denominator. There's a linear function times an exponential, but that's actually not enough to say the radius is infinity. And in fact, the radius can't be infinity. Here's the problem with this function. We plot a number line. We can think of this as the domain. Let me actually write it out slightly differently. Let's think of this as the domain for natural log x. The domain starts at 0. It does not include it. And it goes off to the right. Our power series was centered at 4. Let me see if I can fix this interval. Okay, that looks a little bit better. So our power series is centered at 4. It's guaranteed to converge at 4. But my claim is you can't go any farther than this. The radius should be 4. And the reason is, if the radius was 5 or 4.1 or 4.001, you would go from the center past the domain of the function. You can't plug 0 inside natural log. You certainly can't plug negative numbers inside of it. So because the natural log function has this domain, it implies that the radius ought to be 4. So that's the domain.
Would it have to be less than 4? Because it can't be 0.
Well, we would still say the radius is 4 because in these kind of pictures right here, imagine that this is an open circle here and here, which could happen on these power series. We would still say the radius from here to here is 1/5, even if it diverges here and right here as well. Yeah, go ahead.
You had just colored in the line all the way to 0.
Oh, so you said they colored in the line.
I'm just thinking about over there.
Oh, yeah, I see. So yeah, the domain goes from here to here. But I'm not sure if I totally answered your question though, Christopher.
No, I think you did with the open end. I guess I think of the radius as 4 as being inclusive in the domain, where you're saying it is not inclusive. So like 8, although it is a radius of 4, 8 is not inclusive.
Yeah, exactly. But oh, that's something we would actually have to test to know for sure. We'd have to plug 8 right inside here. We couldn't use a ratio test any longer. We'd have to use some kind of probably the alternating series test, something like that, and determine if that converges or diverges. So in other words, back in section 11.8, let me see if I can get a better example. Not that one, that was infinity. Maybe, oh, that one was at 0. Maybe this one right here. This one had a radius of 3, but when we looked at to the convergence, we found it converged at -3, but diverged at +3. But nonetheless, we still just say radius of 3, since the radius doesn't actually tell us anything about the endpoints for these kind of problems. We actually had to throw in -3, we found it converged as an alternating harmonic, and at +3, it diverged as the harmonic series. And same with this one right here. We know it's going to diverge at 0 because natural log doesn't even defined at 0. But we don't have any information over here unless we do a further test. These problems just want the radius though, so we don't have to test the boundary values. But it definitely is kind of an interesting kind of question. And again, the thing that's also really interesting about these is you can often guess your radius. Other questions or comments so far?
Oh, so we could have determined the radius before evaluating any of this, right? Understanding ln of x and understanding that a equaled 4, we could have figured out the radius
Correct, yeah.
beforehand, I guess. All right.
Yeah, so this is the diagram that says the radius should be 4. And my claim is that is accurate, but we now have to show it by ratio test. So we're going to prove that this little sketch right here is the actual reality for that power series. Other questions so far? Okay, it's good to know that sometimes, even before you launch into the ratio test, you can determine what the answer should be. And it's also surprising when our determination is wrong, right? That means we have something to learn about that problem. So let's see what happens on this one. We're going to take the limit as n goes to infinity. A radius of 4 might be accurate because there's a 4 hanging out right there. So that might be the part that actually gives us what we want here. We still have to take an plus 1. An plus 1 is referring to all of this with a new index, n plus 1. Divide by an. Let's indicate what we're using, ratio test. So now it's a limit as we go off to infinity of, we're plugging n plus 1 in first for the numerator. So we've got -1 to the power n plus 2. Honestly, though, you're taking the absolute values of that. If you didn't even write in the -1 to a power, I'd assume that you just visualized it canceling already by the absolute value. Now, next part is x minus 4, power n plus 1. Denominator, we've got n plus 1, 4 to the power n plus 1. And now we multiply by the reciprocal of this, just as the indexes are. So if we do that, the thing in the denominator would be, or the new numerator would be n times 4 to the power of n. And then the old denominator is now the numerator. Excuse me, the old numerator up here is now the denominator. Better to just say we're taking the reciprocal of that. I think that's the clearest way to say it. So -1, n plus 1 times x minus 4 to the power of n. Now we'll do the careful work of canceling. When we cancel 4 to the power of n, here it just leaves 4 behind. Canceling x minus 4 over here cancels off that exponent. I'll visualize it this way. X minus 4 power 1 is left. I think that's all the cancellations, except that absolute value will wipe out the alternating parts. And left over, we have x minus 4 in absolute value. It's being divided by 4 from this cancellation right here. And then we take the limit as n goes off to infinity of n divided by n plus 1. So this is like the 50th time this kind of limit's come up in this course. The limit of that will be exactly 1, because the coefficient would be 1 over 1 for n and n. So we've got x minus 4 in absolute value, divide by 4 times 1, because we're looking for the ratio test and we're looking for where the power series converges, we put in this conclusion from the ratio test. We want x to satisfy less than 1, so we have convergence. This would then imply absolute value of x minus 4 would be less than 4, which then implies the radius was in fact 4. However, like we mentioned, we know it can't converge at 0, but we don't know anything about right at 8. Let's put this here on the notes. Unknown, convergence, divergence. It requires a further test. You'd have to plug x equals 8 right inside here. If you did that, you'd have 4 power of n. That means this 4 power of n would cancel, and you know what? It would turn into the alternating harmonic series. It looks like it really does converge here. You just have to say that extra information. But in these kind of problems, instructions only ask for the radius of convergence. So if you stopped right here, totally fine with me. Well, any last questions, folks, with dealing with that Taylor series?
Okay, so now with infinite terms, that would model our function from the domain 0 to 8.
Yes, exactly.
But beyond that, it would be completely useless.
Yes, absolutely.
Okay.
Yeah, this one is
Just
an
trying
interesting.
to connect the dots here.
Yeah, I hear you. So beyond, say, 8, like you're saying, this has just no reference at all to the original function natural log 8. But if you're within this domain, it's going to do a great job. You just might need lots of terms potentially. Well, any last further questions or comments so far, folks? Sorry for the random scrolling. Okay, well, let's take a look into the next section then to see what we're getting into. If this can save. Okay, there it goes. What we're looking into in the very next section is going to be applications to these types of Taylor series and Maclaurin series. And the first big application on these notes looks like it's the binomial series. This problem plays a really special role in this class because I do believe this actually came up as a legitimate mathematical question in week 1, 2, or 3. It's a little foggy when it was asked. But this was asked live in class. You could probably dig it up in the YouTube video about this function. It's just really unfortunate that you can take something like, say, 4 plus x squared squared and come up with 16 plus 8x squared plus x power 4 after foiling it. But root 4 plus x squared, you can't do anything with that. And it's almost unfair, right? There's a perfect square that you could square root, and same with the x squared. But with this, there's nothing we can do. It's truly equal to 4 plus x squared to power 1/2. And what can we do to expand this out? Power 2 expands, so does 3, 4, 5, any integer. Negative integers would expand, it would just throw it into the denominator, and then you FOIL the result. But these things have caused all sorts of problems in arithmetic. It's all because of the plus or minus that's in the middle. But what finally resolves all of this weird stuff with square roots is the binomial series. So for our first big application, we're going to find the Maclaurin series to this, 1 plus x to the kth power. K could be, for example, the 1/2 for a square root, a 1/3 for a cube root. Or it could just be 5, and you get the binomial series for 1 plus x to the 5th power. All we have to do is come up with a Maclaurin series for this and see what it comes out as. So let's give this a try. Let's see, I think we have enough time to get through this one. Take f of x equals 1 plus x to the kth power. Because it's a Maclaurin series, we plug in x equals 0. So equal 0 is the center. Plugging 0 for x gives us 1 to the power k. At this point, it doesn't matter what k is. 1 to any power is still just 1. The only way you can break that is if you put an infinity there. That makes it indeterminate. Now, here's the fun steps. Now we're going to start taking derivatives. We go f prime of x, which causes k to become a coefficient. The power on the group 1 plus x is 1 less. And evaluated at 0, this is now just k. Nothing too spectacular. Same idea, plugging 0 here is just 1 to a different power. And then higher order derivatives start to give us a pretty nice pattern. We'll get k times k minus 1, 1 plus x to the power k minus 2. So over here, second derivative at 0 is now k times k minus 1. At this point, we probably do see the pattern, but let's do maybe the third order derivative just to be sure we're looking at the right thing. So f triple prime at x is now k times k minus 1 times k minus 2 times 1 plus x to the power k minus 3. And so now this implies third order derivative at 0 is k times k minus 1 times k minus 2. So we should be able to get a good pattern going from just this right here to write out the general n order derivative at 0. And notice if there's 3 here, we expect 3 factors. And the number that goes here is 3 minus 1. So we just need to transfer all of this into our formula. The generic nth order derivative at the center. So we'll start off just like this. We'll go k times k minus 1 times k minus 2, and you can put in as many of those as you feel like, k minus 3 and so on. Let's go dot, 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 because their k could be pretty large. We don't know. Or rather, n could be pretty large. There could be a lot of factors here. We're putting in n different factors. So we come up to the last one, which is k minus whatever this is, n minus 1. So the n minus 1 here follows this pattern. The only difference is instead of a 3, we're plugging in an n into that location. So that's what the nth order derivative at 0 would look like. It then tells us that the coefficients Cn are k, k minus 1, k minus 2. I'll just put 3 factors on the first part. The last factor, we could rewrite if we prefer as k minus n plus 1. All of it's divided by n factorial. And this time, there's no cancellation, even though sometimes we expect a cancellation with something that looks like it's a factorial. But there's no guarantee this k is giving a factorial type function, because k can now be any real number whatsoever. For example, it could be pi. We could be expanding 1 plus x to the power pi, for example. It's allowed to be anything whatsoever. So what we do is we take all of this and call it k choose n. That's random notation out of nowhere. It might not mean a lot to you, but if you take in probability combinatorics, then this has certainly come up. This is read as k choose n and is called the binomial coefficient. So we've got either the expanded version. I kind of prefer this, to be honest, because we know what we're looking at. If you've seen the shorthand a lot of times, you might find it's a slick way to write it. But in either case, we have that 1 plus x to the power k. Remember, k can be a half, a third. It can be e, pi, square root of 2, anything you would like. It's this power series, Maclaurin series rather, summation from 0 to infinity of k minus 1, k minus 2, all the way down to k minus n plus 1. If you think back, I think all the way to section 11.3, we actually had a power series that was of this format. We had to show convergence, divergence of. It definitely looked weird, and I guess it still is weird. But at least we know where it's coming from now. It came from a binomial series expansion. So the denominator here is n factorial. It's a Maclaurin series, so we multiply by, really it's x minus 0 to a power of n, but we write it this way rather, x to the power of n. And my claim on this one is, this is valid for absolute value of x less than 1. Let's skip those steps because that actually takes a good amount of work to show. But this is not just giving us the radius of convergence. This is the interval of convergence. Absolute value of x must be less than 1, just like with geometric series, this one right here. Oh, well, this just says radius 1. So that's our binomial series. And using that, we can now answer the age-old question of how in the world do you expand root 4 plus x squared, much like you would expand something by foiling it. But now that we have that power series, and we made a pretty big claim there, the rest of the notes in the middle are just showing those steps in one really small spot. So here's the binomial coefficient. The binomial series, if we expanded it out, this is what it would look like. If we prefer our summation notation, this is saying the same exact thing as the line above right here. And this is the super compact way to write it for people who don't mind that extra level abstraction. Again, me personally, I prefer this. Binomial series is weird enough without more random notation. So the convergence of this thing happens provided absolute value of x strictly less than 1. So it will diverge if x is 1 or negative 1, for example. Well, we've got all this machinery now, we're ready to expand out to this thing here. Any questions or comments so far? Okay, the way we're going to do this is very similar to what we've done in the past. So let's pause right here for just a moment, gather up some inspiration from section 11.9. The way we're about to use this formula right up here or down here, depending on which version you're looking at, expanded or the compact one, is exactly the same as what we were doing in this section. We have something like 1 over x minus 4. We want to use the geometric series, this one right here, to write it as an actual legitimate power series, or Maclaurin series is what it truly is. So what we did was we rearrange it. We put it into the right format, so we have a 1 and then a minus. Take this and just plug it right into the formula right above. So that's kind of hard to show unless I expand that out a little bit better. So we get things into this right format, so it's 1 minus something. That something gets plugged in, and then we have our power series. So that's kind of the name of the game in this section. That's why there's a big table down here as well, is because we're going to take these things here and start expanding them using these formulas. So we begin by trying to get it to that format there. We want a 1 to start out. We can make that happen by factoring out 4 from the root. And that does work algebraically because it's a type of multiplication formula. If we factor out square root of 4, we get a 1 plus x squared divided by 4. That actually gave us exactly what we want. We have the 1 and the plus. We have some x. It's different from the other one, but that's okay. Whatever your x is, it's going to plug into that location right there. But notice we're still missing one extra thing. We need to know the value of k on this thing, so it's not a bad idea to call this 2, 1 plus x squared over 4. And this is to the power of 1/2. So this gives us pretty much everything we need to get going. We now have the value for k and all those positions there. And we get this on our next step. It's a summation now as we go from 0 to infinity. Reading up from this line, we're going to get 1/2, 1/2 minus 1, 1/2 minus 2, and so on, all the way down the line until we get here, 1/2 minus n plus 1. Let me actually get that 1 in there. There we go. The whole thing is being divided by n factorial. And x over here is not exactly x. Let's try a little bit better. It's x over here in the formula, but what we're plugging in is x squared over 4. This will be raised to the nth power. And this works as long as, just copying the same verbiage as over here, the absolute value of x squared over 4 has to be less than 1.
We use the 2 for the summation.
Oh, sorry about that. So, oh yeah, that 2 right there. Thanks for spotting that one. That's a not good omission to have there. So double all that, and now you've got the right answer. Mine was half as correct. So we want absolute value x squared less than 1. What we're doing here is coming up with the radius of convergence. So absolute values can be dropped. We can multiply both sides by 4. X squared is now less than 4. Take square roots again, and we get absolute value of x is less than 2. So if we want just the radius of convergence, this tells us radius is 2 by that information so far. And there's not too much more to do. In fact, you could do a lot of stuff to this thing if you really, really wanted to. But I would encourage you, for the sake of working this out as a homework problem and as a potential exam problem, I wouldn't take too much steps with this. It's good to know what it looks like. If you want, you can expand it out like in this format. But we've met our objective. If you want to expand out a square root of whatever is inside like this, here's what you would get. Summation from 0 to infinity. Your x has to be in this range, so it doesn't work if x is 2 or -2, so you have to be picky with your x. But I mean, that makes sense, because if it was, say, well, no, rather, I was thinking this is a negative sign causing a complex number. Yeah, that's just a hard limit to what this method can really do for us. We have a half. 1/2 minus 1 gives us -1/2. 1/2 minus 2 would give us -3/2. Then it would be -5/2. So that's the pattern going on in the numerator. Then we have a 1/2 minus n plus 1. That would be 3/2 minus n. All of which is divided by n factorial. Coming from right here, we also have it multiplied by 4 to the power of n, and x to the power 2n. Radius is 2, just as a reminder on there. You don't have to put it right next to it. But we did it, folks. That's the expansion of the square root there using a binomial series. Well, any questions, folks, with getting that result there? I would say, in my opinion, this is one of those applications where it's kind of a curious application. The real use for this is, well, the binomial series is used in a lot of other abstract things. Sometimes it's used in the proof of other mathematical content. There's not a great application to this other than it's kind of a parlor trick. There's a great way to actually expand root 4 plus x squared. It's that if we really wanted to, we could also expand it this way to make it less abstract. But that's one application. We don't have too much more time, so I just wanted to indicate what the next applications were going to be when we come back on Monday's class. We're going to use all these kinds of series here to essentially redo the last exercise, but for stuff like this. We're not going to come up with the Maclaurin series from scratch. That's a lot of work for this kind of function. We'll use the established Maclaurin series for cosine to find the Maclaurin series for cosine 3x times x squared. We'll do several versions of those and then learn how to integrate things like this. This is the problem our author indicated has no elementary antiderivative, but it does have a power series antiderivative we'll find. Finally, we have this example. If time permits, let's actually do an additional one. Example 6. Show that e to the power I x is going to be equal to cosine x plus I sine x. This is one of the world's most random formula ever, but this is really just a consequence of the power series for e to the x. It turns out e to the x actually has cosine trapped inside of it, as long as you put in a complex number inside there. Extremely bizarre, but that's a cool little trick as well. This is very applicable if you're dealing with complex analysis. But this will be our last problem for the day, since my next problems are a little bit longer, I think. Any last questions or comments, folks, before we call it a day officially?
Are we going to get back to yesterday? You had told us how sinh was equal to, like, it was like e squared plus e. Oh, is that going to come up again too? I found it really interesting how that related. I don't understand it, but.
Well, it doesn't come up officially in the notes, but we can make that a further example. Example 7, show how e to the x and cosh x, sinh x are related. So it's pretty much exactly what example 6 is doing, slightly different kind of derivation. So yeah, we could get right into that one very next. I mean, it's not too different from this one either. Other questions at the moment? Okay, I think this one is a little bit more believable because of the fact that you can always write cosh x as e to the x plus e negative x, like you were mentioning, over 2. So already it's involving e to the x, not the I there, just e to the x. One thing that we're going to discover when you really look at examples 6 and 7, it's the trig functions that are weird, not the hyperbolics. Those are the normal ones that do things that you would expect. Trigonometric functions are very, very bizarre in comparison. But any other questions at the moment? Okay, well, have a great night, folks. If you have any questions over the weekend, don't hesitate to email. I'll be happy to help out. I'll see you all in Monday's class. We'll finish off these notes and then get into chapter 10 if we have time. Oh, and on the Moodle website, I need to extend some of these due dates. It looks like they're not quite accurate at the moment. For example, this one we did not finish this week, so I'll be pushing that due date a little bit. Looks like it'll be due after Thanksgiving